All right, so now we should all see the little record dot, red dot in the upper left-hand side of the screen. And we're recording. And let me go back to sharing my screen. Okay, so now we're back to screen share and recording with screen share. I'm getting good at this. Okay, so just for archival purposes, we're going to talk about mechanics of materials. This is a mechanics of materials refresher, and this is fatigue life, endurance limit, and failure. We've already done the disclaimer, and so we're going to jump right into the origin of the stress strain curve, which is kind of the precursor foundational material to fatigue life. I have already posted a video on YouTube about this, but it's likely that people have not yet had time to watch the video. Just a very quick reminder, this is a stress strain curve, which is one of the kind of fundamental ways to characterize materials, and when those materials then get fabricated into parts, how those parts are going to perform when you put them into a system that is subject to mechanical loads. So stress strain, well, we've got stress on the y-axis, and we've got stress on the y-axis and strain on the x-axis. Stress has units of pressure, so it's a force over an area. Strain, at least for our purposes, is unitless. Stress basically represents how much load is on your part. So the way that it's calculated is we have these samples, they're called dog bones. I think you guys probably did this in mechanics of materials. If not, in my stress strain curve video, I have a video of having this, doing this, but one of these dog bone samples gets clamped into a tensile tester. It gets elongated, it gets pulled, and it eventually gets pulled to failure. And the force that's pulling the shape, that's pulling the dog bone sample, is the force that is the F in the stress. And then the area in the stress is the cross-sectional area of the thinnest part of the dog bone. So that's where this one comes from. And then strain is a dimensionless elongation. So you take however long your specimen is getting as you're pulling on it, and you divide it by the initial length, and that's the strain. And so most metals and some other materials behave this way, where you have it's basically experimental data that generates this curve, but you have an elastic region where basically any deformation that you put into your part is temporary. So both temporary and deformation is linear with stress. So you've got this linear region here. If I'm still in this linear region and all of a sudden I let go, the part will snap back to its pre-stress strain, basically strain of 0. It's pre-stress elongation. And so you don't do any permanent damage to the part so long as you're in this regime. But as soon as you get out of that regime, you reach what's called yield strength. So that's the point where the part starts to fail plastically, meaning you're doing permanent damage. You're permanently deforming the part. If you let it go, it won't snap back to its original size. So we run through a region of uniform plastic deformation, and then we get to this point here at the top of the curve, which is the ultimate tensile strength. It turns out that ultimate tensile strength, UTS, is important for the fatigue stuff that we're about to talk about. So this is really what I wanted to focus on, is that this is the point where the stress that's endured by the part is the highest, right? That's the peak of the curve. And then after that, it's sort of all downhill from there. You're into the non-uniform plastic deformation. And so you start necking, which is the process of this cross-sectional area as a result of plastic deformation starts to drop. The area drops, the force increases, therefore the pressure really increases, the stress really increases, and eventually you get fracture, which is a breaking of the part. So that's the fracture strength is when the part is broken and it can no longer serve its purpose at all. So when we design parts, we really like to stay in this regime, the elastic deformation regime. But as we'll discover here in a second, if you have a part that's subject to cyclic load, it turns out that you end up kind of over here, whether you want to or not, over time, unless you've designed the part very cleverly and used appropriate materials. So let me just pause here for a second, ask if anyone has questions about the origin of the stress strain curve before we hop into the fatigue life stuff. Okay, so I think everyone's okay with this stuff. This, by the way, all of this should be a review, right? You guys have all taken mechanics of materials, mom lab, and then this fracture life stuff. If it wasn't covered in mechanics of materials, it was covered. At least it should have been covered in Mech 1. Okay, so now we're into fatigue failure in metals. So what happens that kind of deviates from this idealization to real parts in the real world, particularly those that are made out of metal? Well, cyclic loading initiates microcracks in metals, and progressive cycling turns microcracks into macro cracks, so small cracks propagate together and become big cracks. And when those big cracks, those macro cracks propagate enough, there is insufficient cross-sectional area in the remaining material to carry whatever load you put on the part. And so eventually you're going to get these cracks propagating together. You're going to get a fatigue situation, and that will cause the part to fail well below the ultimate strength, right? So if you've got the ultimate strength identified here, if you fatigue a part enough, if you cycle it enough times, this point becomes irrelevant, and there's going to be a new ultimate strength point and a new fracture point. And in some cases, that point can even be below the material's yield strength, right? So it can even be below this point, depending on the material and what it is that you're doing to it. So the approach to fatigue failure shows no outward macro scale signs. Failure is instantaneous, sudden, and without warning. So the best example to sort of describe 5, and I think we've now got this sort of as a society solved, but a while back, you guys might even remember, there were a number of airplanes so in the airplane industry, my undergrad is in aerospace engineering. I worked for the Aerospace Corporation for a while, so I know a little bit about airplanes. In the airplane industry, it's advantageous to kind of keep the planes in the air as long as possible, right? People are still flying like MD-80s, right? I mean, they've renamed them, but MD-80s are still in the air, and it's because it's usually less expensive to maintain an old airplane than it is to buy a new airplane. Well, old airplanes and, well, the new airplanes are all made out of composites, but the old airplanes are made out of metal, and they go through all kinds of cyclic loading, right? The wings flap, and not flap like birds, right? Like if you guys have taken any aerospace classes, the wings intentionally vibrate up and down. That's actually part of the design of the airplanes to be able to absorb the load of flight. That the wings are very flexible, and so when you're in flight, they actually will oscillate a little bit. So anyway, that's a cyclic load on the wings of the airplane, right? And the other parts of the airplane have to undergo cyclic loading when they're in flight. Every time you land a plane, that's a cyclic load. Every time you take off, you put the various components through kind of their maximum stress design points. And so airplanes are subject to an awful lot of cyclic loading. And the issue is that you can't actually detect the micro cracks or even the macro cracks because they're usually internal inside the parts. And so you have to go through either destructive testing or like really, really intense testing that's very expensive to figure out if a metal part is suffering from these fatigue cracks. And so there's really no outward signs. And so, this was a few years ago now, but there were a number of airplane accidents that were ultimately attributed to micro cracks that had gone undetected. And so you can't, as an engineer, just look at a part and be like, oh, okay, that's about to fail, and I better replace it with something else, because there's really no outward signs that the failure is about to happen. So so that's pretty important to recognize, is that you can't just look at a part and see that it's about to fail, because everything that's happening to cause it to weaken is happening internally. And then the final point that I wanted to make is that engineers underestimate how many cycles parts actually endure. And there's a cool example of this that I grabbed from, you guys might know Mike Griffiths, who's another one of the design instructors. So this is one that he suggested. So the question is, how many cycles per year does a typical car engine run? And this is a pre-COVID-19 car engine, right? Because my car, for example, is getting about 1 month to the gallon these days because it's just sitting in the driveway. But this is, just sort of a normal pre-COVID American car. And so anybody have any thoughts on what this number might be, how many cycles per year a car engine runs through?
2 million.
Okay, 2 million. Any other ideas? Okay, so we'll, oh, sorry, go ahead.
I was gonna guess 500,000.
500,000. Okay, in the chat, wow, okay. In the chat, we've got 1 billion. We've got 40,000. Okay, so it looks like the bottom of the range is 40,000 and the top of the range is 1 billion, with 500,000, and I think if I remember right, 2 million kind of in the middle. Okay, so so here's how I calculated this. So we're going to assume that a car travels 12,000 miles per year. That's a number that's based on a typical American insurance policy, right? So you can choose kind of the rate that you want to pay based on how much mileage you drive, and this is the standard for American annual mileage in a car based on insurance policies. And we're going to guess. Sorry, was there a question?
Oh, I was gonna say, is it 120 million?
Oh, you're asking, you're saying the number of cycles.
Yeah.
120 million.
Per month?
This is, oh, okay, sorry, I'm probably answering the wrong question. So this is the mileage that a car travels. So this is like the linear mileage on the road that it travels. So I haven't yet answered the question. I'm just setting up how I calculated it.
Okay, sorry.
Yeah, so I might have answered the wrong question, but yeah, I'm not quite there yet. This is the slide with the answer, by the way. It's 36 million cycles per year. But so here's how here, we'll just stay here. So here's how I set it up. So 12,000 miles per year is what the typical American car drives based on, from insurance companies. So that's what they say it is. And they're in the business of knowing, right? So it's probably a pretty accurate number. And then I estimated 40 miles per hour, right? So some of your driving is going to be on the freeway, some of it's going to be on the roads, the surface roads. So you're somewhere between, 25 miles an hour if you're driving in my neighborhood to 80 miles an hour if you're driving down the freeway in Texas. Well, in Texas, it's probably 100 miles an hour. But anyway, so about 40 miles per hour. And we're going to be having our engine cycling at 2,000 RPM. A relatively high gear, and you're not putting too much demand on the motor in my approximation. But I run through the math and I come up with 36 million cycles per year as my kind of rough approximation for how many cycles a car engine experiences in one calendar year. So we had, if I remember right, there was a 40,000, there was a 500,000, there was a 2 million, and then there was a 1 billion. And so let's see, well, if we were playing the Price is Right, the 1 billion actually would have won, right? Because you have to get the closest without going over. I don't know if you guys ever watched The Price is Right. I'm probably dating myself a little bit here, but so anyway, so it's about 36 million cycles per year, at least based on the way that I estimated it. So that's a pretty big number, right? It gives you a sense of how big and so now that we sort of have that number, let's jump into how we use it to figure out the fatigue life for metal components. So what I'm showing here is a strength number diagram or just SN diagram for steel, and the material is important, and I'll talk about that in a little bit. But this is specifically for steel, and just to get you kind of oriented here, on the x-axis, we have the number of stress cycles, n. That's logarithmic. So this n, by the way, is the same n as this one, right? So it's the number of times that whatever part or whatever your system of analysis has gone through a complete cycle. So that's n on the x-axis, and it's logarithmic, right? So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So each one of these lines is 10 times bigger than the previous one. And I think this line in the middle is like halfway between, right? So this line right here that I'm pointing at with my mouse would be like 5 times 10 to the second. This is 1 times 10 to the third. This is 5 times 10 to the fourth. 5 times 10 to the third, 1 times 10 to the fourth, 5 times 10 to the fourth, 1 times 10 to the fifth, and so on. So that's how to read this. And then on the y-axis, we have fatigue strength, which is S sub F for fatigue, and it's in kpsi, which we expect because a strength or a stress, those are all in units of pressure. So psi is the imperial. PSI, pounds per square inch, is the imperial unit for pressure. And then we have a couple of different regimes, which I'll talk about: low cycle, high cycle, finite life, and infinite life. But we'll get into those in a second. So how is this chart generated? Well, you can see all of these little dots that kind of litter their way along the chart, and those dots represent experimental data. So that's empirical data that was collected for a particular sample of steel. And all they did was just put it on a cyclic tester and just count the number of times that they cycled it, and figured out what the fatigue strength was as a result of the number of cycles, and generated this regime and fit a line to it, this regime, fit a line to it, and this final regime. And that's how this was made. So the good news is that you can look up these cycle diagrams, these SN diagrams for a number of different common materials, but you might in your engineering lives encounter materials that that are rare or strange for some reason, in which case you might not be able to find this diagram, and in those situations, well, you've got to do the testing yourself. If you don't know the material is somehow rare or different, then this diagram might not exist for it. Happily, steel is very well known and understood, so there's lots of cycle diagrams for things like steel and aluminum and titanium and so forth. So anyway, how did they generate that curve? Well, what was the experiment? So they ran the experiment. As I mentioned, it's a diagram made up of basically 3 linear fits to experimental data, which I'll talk about in a second. And it's unique to a particular metal and a particular fabrication method. This is also important, and I'll talk about this again in a second. So we have to have completely reversed stress cycles. That's another thing. And what is a completely reversed stress cycle? Well, you take the material and you fatigue it all the way, not fatigue it, you stress it all the way in one direction, and then you relax it, and then you stress it all the way in the other direction. So kind of a good way to describe this. Let me stop sharing for a second. So I've just got a piece of wood here. This is just sort of bamboo, and forgive the knot in the middle, but it's otherwise a uniform piece of bamboo. And so what I'm talking about is, if I were to do this test, I would put it all the way like that, right until it's about to break, and then I would take it and put it all the way like that, and then I would return it to the relaxed state, and that's one cycle, right? So it's in a relaxed state, I bring it all the way down, and then I bring it all the way back up, and you can see it bending, and then I return it to the relaxed state, and that's one cycle. So so let me share my screen again, maybe. There it is. Okay, so a lot of real parts don't undergo a completely reverse stress cycle. So, again, we're taking experimental data and trying to apply it to real life with, in some ways, sort of an incomplete understanding of how the data might actually be used. So it's important to keep this in mind. If you end up with a part that only goes through half of a stress cycle because you just deform it in one direction, you don't deform it in the other direction, this curve is not going to represent adequately the fatigue life of that part. So anyway, keep that in mind. Okay, so there's two regimes. The first is the low cycle fatigue regime, and that runs from 1 cycle up to about 1,000 cycles. And then there's the high cycle fatigue regime, which is everything above 1,000 cycles. And you can see that indicated here, right? So here's the low cycle, which runs up to 10 to the third, which is 1,000, and then the high cycle, which is above 10 to the third. And just sort of spots on the diagram for you to be familiar with, kind of, showing you guys how to use the map here is what we're really doing. Okay, now for steel, there's a knee that occurs beyond which no failure happens. And so you can actually, provided you've designed your steel part, and it has to be steel or similar material, you can actually have a part that goes through an infinite number of cycles and never fails. And that strength is called the endurance limit. So let me point that out here on the chart. So SE is the endurance limit. So that's where the curve basically flattens out, right? And so this is just going to be a flat curve all the way out into infinity. And so if I have designed my part so that I don't put a stress on it that is larger than, it looks like 50 kpsi in this case, right? So a stress that's down here would be lower. I can run this part through an infinite number of cycles and it'll never fail. But that's unique to steel and steel-like materials. Aluminum doesn't behave this way, but at least for steel, there is a fatigue limit, and provided you, an endurance limit, and provided you design below that, you're guaranteed to never have your part fail on you, which is a neat feature. So the finite/infinite life boundary is not clearly defined, but it lies somewhere between 10 to the 6th and 10 to the 7th for steel. So what that means is this is that point, right? That infinite life limit point. So infinite life up here. And so at least in this chart, based on their experimental data, they've found that it's about 10 to the 6th. But for different alloys of steel, or even similar alloys of steel that are fabricated in different ways, this point can move between 10 to the 6th and 10 to the 7th, right? So it can sort of live anywhere in there. And it's up to you as the engineer to identify where that point is for your particular alloy of steel and your particular manufacturing method. But that's basically just what that means, is that there is that knee point, and it lives somewhere from 10 to the 6th to 10 to the 7th. And then the final thing is that non-ferrous metals, especially aluminum, we're engineers and we love aluminum because it's light and cheap. Aluminum and other similar non-ferrous metals have no endurance limit, meaning that their fatigue strength continues to drop with increasing N. And I'll show you guys a plot of that here in a second. But while we're talking about sort of how to read the SN diagram, let me pause and ask, does anyone have any questions about kind of these 7 points and how to read the diagram?
Oh, Professor, I have a question.
Yeah, I'm ready. Go.
So for point 6, does that mean when, say, some engineers doing testing for steel, they only test for, say, 10 million cycles, and if it lasts, it lasts forever?
So yeah, so what they'll be looking for in the test is this change in the data, right? So you can see, like, here's the data that's associated with you're in the high cycle, right? So you've passed 10 to the 3rd, but the fatigue strength continues to drop. And then you'll reach this point that I described as a knee, 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 where that fatigue strength will no longer drop. So yeah, to your point, once they, well, and you can see here, they've obviously measured a couple of additional points just to be sure. But once you see this knee in the data, and you've taken a couple more data points just to convince yourself that your measurement's not an anomaly, then yeah, you don't need to do any more testing, provided you've got a ferrous material, provided you've got steel or a steel-like material. There's no need to test it indefinitely once you've identified where that knee is. Does that answer the question?
Oh, yes, Professor. Thank
Okay,
you.
awesome. Anyone else have questions while we're here? Okay, seems like we're good. All right. So let's move on to aluminum here for a second. So this is a similar SN diagram. Again, I've got cycles, logarithmic cycles on the x-axis, and I've got the peak alternating bending stress, basically the fatigue strength. It's the same value on the y-axis, and instead of looking at steel, I'm now looking at aluminum. And so there's two elements that I want to show you guys about aluminum that makes it, well, two elements that I want to show you guys. One that is uniform across all materials, and the other one that's specific to non-ferrous. So the first one that I like about this particular diagram is that we have the same material, right? It's presumably the same alloy of aluminum, but it's being subjected to different manufacturing processes. So wrought aluminum is basically blacksmith aluminum, right? So it's somebody is taking a piece of aluminum and just hitting it. It's not a forging process, but they're just hitting it and shaping it over and over and over again to get it into its final form. Whereas forging is usually just a one-step. Wrought aluminum is hit several times. And so wrought aluminum has a higher SN curve than does a permanent mold cast aluminum or a sand cast aluminum. Permanent mold casting, by the way, is die casting. So if you guys, when you were young, if you ever played with Hot Wheels cars, those little die cast toy cars, that's a die casting process. And so you basically have a metal mold material that has a much higher melting point than aluminum, and you squeeze a liquid aluminum into this mold, and the aluminum takes the shape of the mold, and then you open up the mold and you pull out your finished aluminum part. So that's a permanent mold cast process, which happens under pressure. And then a sand casting process, again, for those of you who have not taken manufacturing, it's literally what it sounds like. You dig a hole in the sand, effectively, that's the shape of your part, and you pour the molten aluminum into the sand mold, and you wait for the aluminum to go from liquid to solid. So you wait for it to, not dry, but solidify. There we go. You wait for it to solidify. And then you break the sand out from around the part, and you've got your finished part. And so in a way, this is actually pretty cool, because these behave exactly the way that you would expect them to, right? You have a higher failure strength the more that you kind of pressurize or beat on the part, right? So if you've got a wrought aluminum part, you're basically pounding it over and over and over again, and so you're making it stronger as you're pounding it over and over and over again, and so this curve is higher. Permanent mold cast, the die casting process occurs under pressure. So you've got the aluminum, but you stick it into the mold and you pressurize it, and so when it comes out, it's quite a bit stronger over time than a material that's sand cast, where there's no pressure at all, right? You're just relying on gravity basically to hold the liquid aluminum in your sand, and wait for it to dry and solidify. So anyway, it's pretty cool that this lines up. But the point is that we've got the same material, different manufacturing processes, and this is also true of steel, titanium, basically any material that you would make an SN diagram for. You have to be worried about the manufacturing process, because the manufacturing process shifts the location of the SN diagram because of what you're doing to the crystalline structure, to the microstructure of the material, right? Because remember, fatigue is all based on, if we go all the way back here, it's based on the propagation of these micro cracks. And so how you treat the material changes how those micro cracks are going to appear and propagate through. This is super cool. I love this. The other thing that I wanted to show you about aluminum is we mentioned that for ferrous materials like steel, there's an endurance limit, right? So if we go back to steel, this slope reaches 0 at some point, and you basically have infinite life after this. For aluminum, these curves continue downwards, right? So the slopes are non-zero. So in other words, even though the slopes are very slight, as you continue fatiguing aluminum, eventually you're going to reach a point where even if you put very, very little stress on them, they're going to fail, right? And remember, in the aircraft industry, especially in the days before composites, everybody wanted high strength and lightweight. So a lot of aircraft components are made out of aluminum, MD-80 made out of aluminum. And so hence you get those failures that were so prevalent about 20 years ago in the aerospace industry because they made their parts out of aluminum, and poof, they ended up crossing one of these curves because those parts were left in service for way, way too long. Okay, so any questions then about the difference between a ferrous and a non-ferrous material with respect to the SN diagrams? Good so far. Okay, all right. I'm either doing a really good job or you guys are all sleeping. Okay, so how do we come up with the SN diagram, and how do we ultimately use it for something beneficial, right? To estimate the endurance strength of a real part that we would design into a system that's actually getting used. So the way that this is done is that there's a term that's called S prime E. And S prime E is the endurance limit for a very specific type of specimen, which is a rotating beam specimen. And in your mechanics and materials class, you guys have probably already talked about this, so I won't share the geometry with you. You can look it up. But there's a very specific specimen for which this very particular S prime E SN diagram is developed for. And once you run the experiment based on this particular specimen, this particular geometry, you can back out everything else that you need to develop, at least an approximated SN diagram for more complicated parts. So how do you find the endurance limit for this very specific rotating beam, this S prime E? Well, there's a formula for it, which is here. So we take the minimum ultimate tensile strength for your specific material and we plug it into basically this formula. And now to kind of put the pieces together to remind you of what this is, this ultimate tensile strength, if we go all the way back to the beginning, remember, here's our stress strain curve. Here's the ultimate tensile strength, right? So it's just one point on this curve. So you can actually back out a reasonably good approximate SN diagram by just taking your material of interest, putting it into this particular rotating beam specimen shape, and running that beam through basically a failure process where you determine what the ultimate tensile strength is. So you can come up with an approximate SN diagram really just based on, like, I don't want to say one experiment because you'd obviously want to repeat the experiment a number of times to make sure that it was correct, but a very few number of experiments and you can get a good sense of what this diagram looks like. So once you've got that ultimate tensile strength, you plug it into this formula and out pops this S prime E, this endurance limit for rotating beam specimen. So if your ultimate tensile strength happens to be below 200 kpsi, then, oops, sorry, I've got that backwards. Yeah, okay, yes, below 200 kpsi, then you just use 1.5 times the ultimate tensile strength, and so that gives you S prime E. If it's above 2000 kpsi, then you just use the value of 1000 kpsi. And when I initially saw this, I was really confused. I'm like, why are there these two different lines here? And when you do the math, it turns out that 2000 kpsi, which is imperial units, is the same as 1400 megapascals, which is SI units. So these two are the same value. One is imperial, the other is SI. So that confused me for a really long time, but now I'm glad I can understand and explain to you guys. Okay, so once we've got this S prime E, then we can create the rest of the diagram, right? So SE is here, or S prime E is here. And what we need to do is come up with an expression for this first part of the curve, so the low cycle portion of the curve. And then we have to tackle the middle portion of the curve, so the high cycle portion of the curve where we're still losing strength as we increase the number of cycles. And then ultimately we need the endurance limit. Well, okay, we've already got the endurance limit because we just calculated it there. But I'll show you how to stitch all three of those together. So first piece of information we need is a value called S. S is the fatigue strength fraction. And the fatigue strength fraction is tabulated for a number of materials. This is the one for steel. So on the x-axis, we've got the ultimate strength, which remember is the thing that we, if I go all the way back, that's the same point, right? So we just literally need 1 point to calculate all of this stuff. Right, okay, so that's the peak of the stress strain curve is this value here on the x-axis, and then on the y-axis is this value F, which is really just an empirical correction factor, right? We're engineers. To learn what we need to learn, we run experiments, collect data, and we fit curves to the data, and then say that that's the way that the world is. And once you figure out a theoretical way of describing something that's proper, well, it's no longer engineering, then it's physics, right? So this is still an engineering approach because this F number is empirical, based on experiment rather than based on some underlying theory. So you get this diagram, and then you come here, right? So we're looking for the equation for this line, which is the linear part for the low cycle. So to define a line, we only need 2 points, right? 2 points make a line. And so what's the first point on the line? The first point on the line is at the number of cycles equals 0, right? So you put your sample through 0 cycles, and you've driven it all the way up to failure. And that's the failure strength, the fatigue strength for 1 cycle, right? As if you just bend it to the point that it breaks. So that's that point. And then the other point is, remember, the end of this low cycle regime happens at about 1000 cycles, so 10 to the 3rd cycles. And so the other point is an X value of 10 to the 3rd and a Y value of F, which we just determined before, multiplied by the ultimate strength of the material, right? So again, you only need this one value, ultimate tensile strength, and you can come up with everything else. So I've got now 2 points, and I just draw a line that connects them, and that's my curve. And then here's the actual equation for it, right? So the fatigue strength is going to be basically greater than the value of this, which is the equation of that line. So that's how you get that portion of the curve. Okay, so any questions about how I get that part of it? Okay, so far so good. All right. The next part of the curve, I'm gonna kind of skip over and come back to this, but remember, we're just stitching together 3 pieces, right? So I now know this point of the middle part of the curve because I calculated it previously. And all I need to know then is this point of the curve to get this portion of it, the middle portion of it. So we'll come back to the middle portion here in a second. The final part of the curve, well, we already know how to calculate that, right? Because we talked about it. So the fatigue strength upper bound is given by the specimen endurance. This is the endurance limit that we calculated before based on just knowing the ultimate strength of the material. So you get that value, you plug it in. That's the SE value for that particular material. And then remember that this SE value occurs kind of where this knee is. Right, so where this knee is. And so if we remember back to the description, that knee, that infinite finite life knee, occurs somewhere between 10 to the 6th and 10 to the 7th. And so for our purposes, we're just, because we're just now kind of creating an SN diagram based on one measurement, we are going to place that spot halfway, right? So 5 times 10 to the 6th, halfway between 10 to the 6th and 10 to the 7th. And that's going to be the location of where we transition from the linear portion coming down to where we've got basically infinite life. And so that gives us this spot. And now all I have to do is connect those two lines, right? So I've got the spot, connect those 2 points. I've got the spot up here. I've got the spot down here. I just draw a line between them and I'm good. So that gives me the middle. So any questions on the middle? How did I get that? Okay, sounds like good on that one. And then you guys already know how to calculate this, right? So we've talked about this one already. You determine the ultimate strength for your part. You plug it into this equation, deciding whether it's larger than or smaller than 200 kpsi, and out pops S prime E, and that gets you that value, which at least for ferrous materials runs off into infinity. For non-ferrous materials, I've had this question before. How do you determine the slope of this line? You have to run experiments, right? You have to determine the slope of the line by just taking your part and running it through experiments until you actually get to failure. And that's the only way that you can know, whether these slopes are constant, whether they continue to curve, like what exactly they look like. But for ferrous materials, we have this nice flat line here at the end, which gives us the ability to design things that live below this line that will last forever. Okay, so we've got now the 3 pieces of the SN diagram for ferrous materials. But remember, we've generated this curve for a very particular type of specimen. So a stainless steel specimen that has just basically a shaft, a rotating shaft. And so how do we then extend this model, this approximation, to give us some sense about how to design real parts, right? Because you guys aren't all going to just design a bunch of rotating shafts for the rest of your careers. You're going to be designing, parts that bend and parts that flex and parts that do things other than just get cyclically, cyclically loaded in rotation. And so the way that we do that is we modify this SE prime value by multiplying it by something called a Marin factor. And these are just correction factors, right? So I always tell you guys, I'm a fluids guy, and fluids is full of correction factors where we take idealized equations and then we fix them so that they behave correctly for the real world. Marin factors is just the mechanics and materials equivalent of that. So these are set up so that they just multiply by S prime E to give you SE, which is the real endurance limit of the true part that you're trying to create based on the geometry and the treatment of the part based on all these Marin factors. And the other thing that I should mention while we're here is that this all represents an upper bound, right? So it's a fatigue strength upper bound, in that once you calculate the SN curve, at least the approximate SN curve using this technique, it's a bound, right? So you've got to make sure that you're designing below this bound, not above this bound, or else parts are going to fail even before you expect them to. So the Marin factors. We've got a bunch of different correction factors. These comes out of Shigley, and I'm sure there's Shigley's, and I'm sure there's more. But surface condition modification, size factor modification. So it turns out that small parts get a size penalty associated with them. Load modification factor. So if you're putting a part in bending rather than rotation, you get to calculate a KC for that. Temperature modification. So if you have a part that's, oh, sorry, go ahead. No, was there a question or someone just accidentally hit the mute button? Oh, okay, I guess we're okay. So if you're operating your part at an elevated temperature above room temperature, you have to modify for that. And then we've got reliability. So if you want a higher factor of safety, a higher reliability, you can make a correction for that. I love this one, miscellaneous effects modification. It's like basically everything that doesn't fit somewhere else ends up there. And so you take the S prime E that you calculated using the rotary beam test specimen endurance limit, which we've already talked about. You multiply through all of the relevant Marin factors, and you get the endurance limit for the actual part. And then once you have that, you can go back through this exact same process that we described, find that point, and reproduce the actual SN diagram for your part, where SE is not S prime E, which is the idealized one for the specific test specimen, but it's the one that's now modified for all of the changes that you made to get from that original test specimen shape through the Marin factors into the configuration of your final part. I do have these. So let me see if I can pull these up here. I think we finish at 12:15, so we've got just a few more minutes. So let me just pull these up to show you. Maybe. Nope. Let me try again. Oh boy. One more attempt here. There they are. Okay, so let me share this. Bing. Okay, so this is pulled right out of Shigley's. So you can see this is the exact same equation. In fact, I basically stole this slide from Shigley's. But these are all of the different Marin factors, and they each have their own weird little kind of technique that you have to use to calculate what the value is. And I'm not going to go through them in detail because you guys have presumably already done this in Mech 1, and you can run through these yourself. I have posted this set of slides up on Canvas so that you guys can see how to do all of these if you need to do them for your own design calculations. But you can see we've got KB, which penalizes parts for having a particular size or shape. KD, which penalizes parts for operating at higher than normal temperatures. That's still KD. KE, which if you're changing your reliability to something other than basically 100% reliability or 99% reliability, you can make those modifications. And then the miscellaneous factor here, which I guess we've got to look up in the book because I'm out of slides. Okay, so that's endurance limit and the SN diagram. So in the last minute or so, does anybody have any questions I can answer about this content? Okay, sounds like no. All right. So awesome. So I do have posted up on Canvas. Let me share my screen one last time. I do have posted up on Canvas an example problem that goes through how to generate the SN diagram and then how to determine like basically the lifetime of a sample artifact. And I'm super excited about this one. The research that I do now, the experimental research, is Tesla turbine research. Tesla turbines are bladeless turbines that can withstand two-phase flow. So you can put basically wet steam into them. And you guys, if you took and survived thermal, you know, if you put wet steam into a conventional turbine, it's over, right? The turbine gets destroyed. But Tesla turbines don't care. You can run wet steam through them and they don't mind. So they're particularly interesting for scavenging operations. So for example, if you've got like a solar fired boiler, it's really difficult to do reheat with a solar fired boiler. So you end up with wet steam, and you can't generate power from wet steam with a conventional turbine, but you can with a Tesla turbine. I actually was an engineer at a startup company that did that. We had a commercial scale power plant that was a solar fired Tesla turbine driven power plant. Anyway, their hallmark is that they spin really fast. And so a lot of times when engineers design them, they forget how fast these things are spinning, and they end up failing catastrophically way before people expect them to fail, because people don't remember that they're spinning so fast that they develop a really long or really big number of cycles over a small period of time because of how fast they spin. So I've got a video posted on Canvas where I walk through basically how to use the technique that we just went through to describe the SN diagram for this configuration, and then how to solve for basically the lifetime of it. So I encourage you guys, after this is over, if you've got some spare time, to pop onto Canvas and watch me kind of walk through how to do this, do it in parallel yourselves. And that'll be kind of the cherry on top to make sure that you guys are experts in fatigue life, so that we can move forward with that as we move into the major design project. Okay, so we're right at the end. It looks like 12:15 on my clock. So I'll stick around for a couple of minutes, but let me stop sharing and stop recording.